Hello and welcome to the channel ED Technology. In this series of lectures, our topic is non-homogeneous higher order ordinary differential equation, and our today's topic is shortcut method 1 for the PI. PI stands for the particular integral. So let's go for our today's example. This is our example. We need to solve a differential equation of the form y double dash minus 3y dash plus 2y is equals to 3 e raised to x. Now one can easily observe that this is second order ordinary differential equation, as well as we are having a forcing function over the right hand side, so this is non-homogeneous higher order ordinary differential equation. And the solution of non-homogeneous higher order ordinary differential equation includes two parts. Its solution will have two parts. The general solution y is equals to yc plus yp. Here yc stands for the CF and yp stands for the PI. So what we need to identify, we need to have yc as well as yp for the solution of this differential equation. So let's start. We will start with the yc. For the yc, we will have its auxiliary, we need to have its auxiliary equation, and for the auxiliary equation let's have its decoded form. So the differential equation is y double dash minus 3y dash plus 2y. Its decoded form will be something like this. This will be d square y minus 3 dy plus 2 y is equals to 3 e raised to x. Now for the auxiliary equation, we need to have our f of d. For that I am presenting the same equation in this form: d square minus 3d plus 2 all into y is equals to 3 e raised to x. Now the form of auxiliary equation, we all know that the auxiliary equation is f of d equals to 0. We need to equate f of d with 0. So right now f of d is d square minus 3d plus 2. I'm equating that particular with 0, and now we will go for the roots of this auxiliary equation. The factorization of this quadratic equation will be d minus 2 and d minus 1. So d minus 2, d minus 1 both will act as a factors of this quadratic equation, and with the use of that factors we will have its root. So roots are 2 and 1. One can observe the roots are real and non-repeated. Both these roots are real and it is non-repeated. So using that, we'll list out yc, which is the first part of the solution. Yc, we are having two real roots, so I will use two arbitrary constant. My first arbitrary constant is c1 e raised to 2x, and second arbitrary constant is c2 e raised to 1x, that means e raised to x. So this is my CF for this differential equation. Now we are moving for its yp. Yp stands for its particular integral. Now for the particular integral, we know that the formula is yp equals to 1 upon f of d into r of x. Right now our forcing function is 3 e raised to x, that will act as a r of x, and we are having a f of d. F of d is d square minus 3d plus 2. And forcing function is 3 e raised to x. Now as per our shortcut method 1, what we are supposed to do, we are supposed to compare our forcing function with e raised to ax. Now if I'm going to compare e raised to x with e raised to ax, my a will have value 1. Here coefficient of x is 1 and coefficient of x is a. By comparing both these, I need to have a. So my a is 1 right now, and as per my previous video, as per our shortcut method 1, what we are supposed to do, we are just supposed to replace d with a. Now observe, if I'm gonna replace d with 1 over here, because I'm having a as 1, if I'm gonna replace d with 1, then denominator will become 0, because 1 is one of the root of this f of d. So to bypass this confusion, what we need to do, we need to modify our 1 upon f of d. Now how to modify our 1 upon f of d? Now in this way, for the modification, we will multiply x in the numerator and we will differentiate the denominator with d with respect to capital D. So differentiation of d square will give us 2d, and differentiation of 3d will lead us to 3. Differentiation of 2 constant, derivative of any constant leads to 0, so it will be x upon 2d minus 3. My forcing function will be as it is, 3 e raised to x, it will be as it is. Now what we had done, we had just modified our 1 upon f of d in such a way that I had multiplied numerator with x and I had differentiated the denominator with respect to capital D. Keep this thing in your mind. Now after having modification once, we will follow the same process. Once again we will try to replace d with 1. A right now, a is 1, so I'm going to replace d with 1 under the condition if my denominator is non-zero. Now if I replace d with 1 over here, then it will give me 2 1s are 2 minus 3. It will be non-zero number, so I can do that. So now I'm replacing denominator with 1, denominator with that particular value of a, that is 2 1s are 2 minus 3. The forcing function will be as it is, 3 e raised to x, and solving this we will have x 2 minus 3 gives me 1 minus 1, and the forcing function will be as it is, 3 e raised to x. Now this will give me minus x and multiply with 3, minus 3x e raised to x. So this will act as my yp. So this is my yc for the given differential equation, as well as this is yp. So the general solution is y equals to yc plus yp. This will lead us towards the final answer for this question, yc plus yp. So general solution will be y equals to c1 e raised to 2x plus c2 e raised to x minus 3x e raised to x. So this is the way we can solve a non-homogeneous higher order ordinary differential equation if our forcing function is exponential form, in our next video we will discuss our shortcut method 2. Thank you very much.